Greetings from Avarta. Myself, Krishna Chandran. I'm here to give a talk about my company, Avarta IT and Design Solutions Private Limited. The key players include myself. I have done my master's and PhD from mechanical engineering at the Indian Institute of Technology, Kanpur. I focus on design process using computational fluid dynamics, more popularly known as CFD. The next key person is my wife, Radhika, who has done her master's in design for retail experience from National Institute of Design, Bengaluru. I will be talking about CFD aspect in this presentation. This is located in the Pathanamthitta district of Kerala, India, a lush green campus which is also very near to the banks of the river Pamba, which is very popular and sacred, especially for the Sabrimala pilgrimage. So, what are the objectives of Avarta? So, how did the name come about? So Avarta or Avarta is pronounced Avarta is a Sanskrit word that generally means whirlpool, vortex eddies or revolving that closely connects with the fundamental structures involved in the subject of fluid flow or fluid dynamics, which is one of the major areas that the company focuses. Initially, we are uh, we are planning to start it as an IT and design consultancy firm where we particularly focus on the computational fluid dynamics design process for aerospace, mechanical, electronic, biomedical applications, and as well as the retail experience and company branding from the design side. And apart from the consultancy work, we are also thinking of upskilling programs. So these subjects like specialized subjects like computational fluid dynamics and design process may not be available at the university levels, and people may not be able to avail these courses that easily. So we are thinking of upskilling programs for this to enhance their skills. So for that we will be providing pedagogical lecture series. We will be conducting seminars, workshops and podcast with experienced people in this domain. So what exactly is computational fluid dynamics? So this is a subject that deals with the prediction of fluid flow combined with heat transfer, mass transfer, chemical reaction, etc. So anything that deals with the flow physics governed by a set of mathematical equations, also known as the Navier-Stokes equation, which are then numerically evaluated using a set of computer programs, forms the kernel of CFD. So basically, it's a design process involving computer simulated programs. As shown in the slide, it typically has three stages. The first one is a pre-processing stage where we give the geometrical details and the rest of the details to the solver. And the solver is a set of computer programs that numerically solves the governing equations of any flow. And the third stage is the post-processing stage. That is, once the solver completes your simulation, you have to visually interpret the results. So there are softwares that can visually interpret your results that are obtained from the simulations. If required, if the required criteria are not met, then the whole design process is repeated until we get the desired output. Before we go to the application side of CFD's design process, I thought of putting this picture in the presentation to talk about what is known as the nature-inspired design. When you talk about CFD design process, one of the most important applications that is dealt by CFD is in the aerodynamics design. Here is a picture of a prayer green falcon, which is the fastest creature on Earth, which has millions of years of evolutionary design as its backing. When the bird is hunting, it climbs to one altitude, and as soon as it spots its prey, it goes to what is known as a nosedive, which is at extreme speed of around 350 kilometers per hour. For any living creature at that speed, you need to have an extra set of protections, else the air at that pressure may sweep in and damage its lungs. So hence, a small nose cone or tubercles, as you can see here in the arrows, as shown by the arrows, or that can divert the air without effect directly going into the lens. The same principle has inspired aerodynamists to design the nose cone in the engine, which when the flight goes at such high speed, air pressure should not damage the engine components. Inspired designs and CFD applications. The design of bullet trains, also known as Shinkansen, developed by the Japanese engineers, was inspired by one such design. It was noticed that when the bullet train entered the tunnels, there was a loud boom, also called the tunnel boom, as soon as it exited, because of the high pressure wave it creates when it is inside the tunnel. The engineer was inspired to redesign the nose of the train when he observed that a kingfisher with his long beak could easily plunge inside the water from air. With very little splashing of water, it could easily catch its prey. Similarly, CFD is also used to model and reduce the underwater drag experienced by underwater vehicles by observing different modes of swimming and its nature of design. The shark fin inspired design is used to reduce the drag and increasing the lift as shown in the figure. Other forms of nature-inspired design include design of textured surfaces that helps it to become a hydrophobic or hydrophilic surface according to the demand. Uh, Hydrophobic means it's water repellent, as we can see in the lotus leaves, insects walking on the water, ducks swimming. It's all because of the nature of their body is hydrophobic or water repellent. Now, CFD is now widely used in tandem with manufacturing science for the design of textured surfaces. Is also widely used in space and related applications. By launching the vehicle acoustic environment and acoustic loading predictions, if you can see this tank sloshing is another important way where CFD can be of help. You can see the difference there is very little difference between the experimental and the CFD simulations of rocket fuel tank sloshing, which is not permissible when the rocket is in the transition mode. So, and also in the lander soil erosion and impact, people believe that once you don't have an atmosphere, then CFD is no longer being used. But that's not the case when you are outside the planet. Certain applications like lander soil erosions also is very crucial. So CFD is widely used in such situations as well. And also in certain applications like the radiation and space nuclear effects on electronic devices and circuits. And the most important of all the devices that are being that in where CFD is being widely used are the designs of pumps and turbines. These turbo machines are widely, I mean, very CFD is now being very widely being used in this type of and the design of these pumps and turbo machines, and it's gaining a lot of popularity, and it has cut down a lot of cost when designing these kind of flow devices based on the demands. Energy sector. CFD is widely used in the design of wind turbines for thermal management in nuclear power plants and battery electric vehicles. Efficient cooling is important in battery electric vehicles for optimum performance. Due to the space constraint, it becomes a challenge for efficient design, where CFD could actually cut down the overall cost of design. CFD is also used in the design of wire mesh gauze, making it hydrophobic so that water does not stick on its surface and can be used for efficient water harvesting in arid and semi-arid areas. The last picture shows the CFD simulation of the heart. CFD now is widely being used for the design of biomedical devices that assist in the overall healthy functioning of the human body. As mentioned in the previous slide, CFD is widely being used now in biomedical applications. One such area where I also happen to work is in the application of CFD to understand the hemodynamics of cerebral aneurysm. An aneurysm is an arterial disease where the arteries lose its elasticity and become rigid, which in course of time may result in bulging of certain areas. If medical intervention is not made promptly, it may result in the rupture of the blood vessel, which can be fatal. For doctors such as neurosurgeons, MRI images give the geometrical details of aneurysm, such as the size and its orientation, but not the wall loading or the stress applied on the walls of the aneurysm due to the blood flow. CFD can give the exact values of the wall loading parameters such as the wall shear stress and the oscillatory shear index by correctly specifying the flow conditions. How it's done is that we take the MRI images of the brain and extract the aneurysm section using imaging tools, then mesh the geometry and run the CFD simulation by specifying the flow conditions at the boundaries of the geometry. The results are then post-processed to know the exact values of wall shear stress and other clinically relevant parameters. Well, an AI ML CFD trained model could predict these parameters much faster, which I will talk about in the next slide. Well, CFD simulation takes its own time depending on the number of mesh cells that are used for the simulation. It may even take weeks to get a converged solution. Hence, industries have shifted their focus in generating reliable AI or machine learned CFD models. Keeping aside the time taken to train the ML models, this is a cost effective solution. These kind of models help neurosurgeons to prescribe better and timely treatment for aneurysms. Hence, industries that focus on manufacturing of medical imaging machines such as MRIs are keen on integrating such AI ML based CFD models into their hardware. In this way, it will not only give the geometrical details but also the wall loading parameters through a single scan itself. Well, the question that ponders in everybody's mind right now will be why CFD? Well, to make it simple, it is to bring down the cost. Building an experimental test facility can cost in millions, whereas a workstation with a decent configuration can tackle many medium to large scale problems. However, there are caveats which need to be taken seriously. It's not as simple when you say that the time taken for a design process is equal to time taken for the CFD simulation. The major time taken may be elsewhere, could be perhaps in the meshing of the geometry. From a CFD solver's perspective, the design time can be equated to the simulation time. We can bring down the computational time by various means. One such process is by parallel computing, where you increase the number of CPU or GPU cores, but consequently, it will increase the actual cost of the machine. We need to make sure that a balance is maintained. There is considerable advancement in the field of quantum computing in the last decade. In this new age of computing, the future of CFD2 will heavily depend on the progress made in the field of quantum computing. We can see here on the slide why industries are pumping in money into the CFD market, as they find it really lucrative and reliable at the same time. Both the global market and the Indian market show a similar trend in market projection in the next 8 to 10 years. So what do we do with CFD at Avarta? So, as specified, as mentioned before, we do want to take up the consultation work with the use of listed software uh, in this given in this slide. And second is the upskilling part, which I have talked about at the beginning of the presentation. We want to keep an open mindset when we target a problem that is related to CFD, which means that we do not want to focus on specific software or CFD, but want to keep a broader mindset as we believe that a single software will not be able to tackle all the problems. Hence, it is important for us and also to the people that we train to keep an open mind and be adaptable to handle all types of problems related to CFD. And with that, I would like to wind up my presentation. Please stay tuned to our channel for more exciting videos, and please like, share, and subscribe to our channel. And thank you very much.